I'm here going to tell you about the FLUX pipeline for MEG analysis. So this pipeline is just out in a paper in NeuroImage, and we also have a website where we explain more about the pipeline and also provide codes and examples for how to use it. Several people have been involved in developing this pipeline. In particular, Oscar Ferrante and Ling Louis have been important for the MNE Python part of the pipeline, and Thomas Minerik has been important for the FieldTrip part. So this pipeline has grown out of collaboration in the context of the COGITATE consortium. So this is a consortium involving multiple groups across the globe, and the idea of the consortium is to test different theories on consciousness. So the goal of my group has been to collect and analyze MEG data, testing different experiments and hypotheses, and the same hold for Huan Lu's group at Peking University. So since we are two groups involved in this project and we need to align our approaches, we figured out that it was very convenient to develop a common pipeline that then now has resulted into the FLUX pipeline that we have published. Furthermore, several people in my group here at the CHBH, the Neuronal Oscillations group, have been involved in doing the development. So why did we develop this pipeline? Well, this is because we think that MEG analysis is facing multiple challenges these days. First of all, there's more and more projects involving multiple sites where the data are recorded. So of course, when you are recording data from multiple sites, it's important to have standard approaches not only for the data collection, but also for the analysis. Furthermore, our community is growing. There's more and more people that need to be trained on MEG analysis. Of course, if you have a standardized approach to some of the basic steps of MEG analysis, that helps this training. There's also the issue of reproducible science. So, of course, what we do in one group in terms of MEG analysis and conclusions, that should also be reproducible in another group. Given that there are so many approaches to data analysis, this hampers this reproducibility. So again, we will benefit from standardization. So now there's other challenges when doing MEG analysis. One of them being that there are many toolboxes to choose from. We are so lucky there are several excellent toolboxes out there, but it's not always clear which toolbox one should choose for which project. Furthermore, when you have settled on a toolbox, the problem is that you might be faced with many options for doing similar analysis. So that means two well-trained, excellent researchers from different labs approaching the same data set might come up with different approaches, and this for having the same analysis goal. And of course, that also produces a challenge for reproducible science. So we want to sort of narrow down the options for the data analysis by providing a concrete pipeline for which step to take. So there are several excellent papers out there defining pipelines. However, these papers stop short of providing the actual code for doing the full analysis. And this is that gap we want to fill here. So basically what we have done is to provide code for how to analyze data in MNE Python and also in FieldTrip. What we also do is to provide suggestions for text that can be used in manuscripts and also for pre-registrations. So again, if you look at papers from different labs, a problem is that these labs or groups might be reporting quite differently the way they are doing the analysis. So again, by providing examples for what to report, we hope to strengthen the game there. Furthermore, pre-registrations are becoming increasingly important, also in the light of open science. So pre-registrations are difficult in a sense that a lot has to be defined before submitting them. And we now think by providing suggestions for the analysis and also text for that, it should lower the threshold of doing pre-registrations. Furthermore, what we also provide is a data set that can be used in training and education. So when you go to the NeurOSC/FLUX website, what you will find is a description of the pipeline in general. And here is just the sections being concerned with MNE Python. And what you find here is different chapters, and these different chapters point you to different part of the analysis. So of course, first there's a general introduction explaining how to install and so forth, and then there's all the steps required for taking the data all the way to source analysis. And there's also a graphic illustration here of these steps. Of course, first there's the pre-processing, including noise reduction and artifact reduction by ICA and so forth. After that follows the trial segmentation. And what you then have is how to calculate event-related fields, time-frequency representation of power, and multivariate pattern analysis. And finally, then the source modeling that allows you to localize where in the brain the activities of interest are being generated. So the pipeline here is for the MNE Python part implemented as scripts written in Jupyter. And this is very convenient in the sense that if you now click on one of the links, one of the chapters on the website, it takes you to a GitHub site where you find these Jupyter scripts. So these Jupyter scripts allows you to provide documentation and justification for the different steps in the analysis. And then what you also find is the code. And within these Jupyter toolboxes, it's then possible to directly execute the code. What is also very convenient is that these Jupyter scripts produce graphical outputs. So that means you can change parameters and directly see what are the consequences of that. Furthermore, it's also very convenient for us because we can simply just provide a link to a website providing these Jupyter scripts, and there we have both the code, the documentation, and the graphical outputs. As I mentioned before, we also provide examples for what can be used in pre-registration and publication. So this means that you can simply copy-paste, if you will, this text into your paper or your pre-registration, or you can modify it according to your needs. But again, the aim here is to increase the reproducibility across labs by providing some suggestion at least for what should be reported in papers. As I mentioned, there's a dataset associated with the FLUX pipeline. So this is based on a simple paradigm where participants are asked to attend left and right, and after a good second there are some movement gradings coming on. So the idea here is that this paradigm produces very strong modulations in the alpha band. The movement gradings also produce induced gamma band activity, and at the same time there's also reliable event-related fields and also button responses. So basically we have modulations of alpha and gamma oscillations and event-related fields, and this is something that we then can try to analyze and eventually also localize the sources of the activity of interest. So here's an example for what some of the outputs might look like. So this is the analysis of the gamma band activity, and what you can see is that the gradings here produce reliable gamma band oscillations. What we do is that we provide the scripts and the settings for doing this analysis in MNE Python, but also in FieldTrip. And what you should appreciate here is that despite the different color maps, the output is very comparable, right? So we have tuned the two analysis approaches to provide very similar outputs. The same holds for the source modeling. So this is the sources of the gamma band activity, and again, when using MNE Python and FieldTrip, we get very comparable results. So just a few words on rank reduction. I mention this because when using the SSS algorithm for reducing artifacts, there has been the issue that this algorithm is reducing the rank of the data as well. So that has posed some problems for doing beamforming, in particular when doing the pseudo-inverse of the covariance matrix, because it's rank deficient. Now it turns out that one solution to this is to use the truncated pseudo-inverse. MNE Python can do this directly, but we also provide scripts for how to do this with FieldTrip. So at least just in our eyes, there's no longer a problem using SSS together with beamforming, when simply using this approach of the truncated pseudo-inverse. Something we are very excited about is to use machine learning approaches in our data analysis. And lo and behold, there's a lot of papers out there using different kind of classification algorithms, but also RSA analysis for analyzing MEG data. So what we provide is the guidance, at least in MNE Python, for how to do classification. And MNE Python is integrated with the scikit-learn toolbox or module. So this is very convenient because there's a lot of developments in machine learning and classification algorithms. Some of those are implemented in the scikit-learn module, and MNE Python can very seamlessly apply these developments. So then you might ask, when doing your MEG analysis, should you be using FieldTrip or MNE Python? I should also mention here there are other excellent toolboxes, some being Brainstorm, and there's also the GLM toolbox. Well, what should you choose? Of course, it's a matter of personal preference, but in my group, we are switching to using MNE Python. And this is motivated by the fact that we have found that what can be done in FieldTrip can also be done in MNE Python. However, we want to future-proof our research. And as you might know, Python is free, so that also means that there's a larger community that can be using our developments. Furthermore, Python is taught as a basic programming language, at least at our university, but also at many other universities. So that also means that it's easier for new researchers getting into MEG research to do the analysis because they already have the Python skills. Furthermore, as I mentioned before, we are very excited about using machine learning tools for MEG analysis, and of course this is becoming more and more popular, as evidenced by many papers on that. As it turns out, MNE Python is integrating the scikit-learn module that has a lot of excellent machine learning approaches. Finally, when it comes to statistics, Python has also different modules, really good modules that directly can be used for statistical evaluation. Anyhow, so what future directions might we take with this FLUX pipeline? Well, first of all, we want to embrace the MEG bits format. We probably should have done this already, but we simply ran out of time. But in the next iteration of the FLUX pipeline, we want to integrate this. Furthermore, there's OPMs. People are very excited about it. OPM is sort of OPM application in MEG research. We also setting up an OPM lab here. We want to extend the FLUX pipeline to embrace analysis of data from OPM sensors. Furthermore, we want to develop the group analysis and also resting state analysis based on hidden Markov models. And what we're also doing here locally is rapid frequency tagging. We want to develop the scripts for doing that, so also make that approach more applicable for other research groups. And finally, we are in the process of developing courses, both online but also in-person courses for using the FLUX pipeline. But this is all to be said that the FLUX pipeline is not meant to be static. It will be under constant development. So I'll end here and just encourage you to try out the pipeline. You can find the link here where you can read more about the pipeline, but it will also take you to the example data set and also the scripts.